Hi everyone, and welcome to today's presentation of paper Intermittently Powered Bluetooth that works. This paper is presented by students and professors at University of New. In near future, we are looking at massive influx of Internet of Things, gadgets, and ranging from sensors to smart home devices. But here's the snag: most of these devices rely on batteries, which means we are stuck with the hassle of replacing, monitoring, and recycling them. It's not just a headache, but it's also a strain on our wallet and the environment. To tackle this battery sustainability issue, scientists are diving into the world of battery free IoT systems. Instead of relying on traditional power sources, these systems harness ambient energy like sunlight or radio waves to keep things running smoothly. It's a game changer that we could make our IoT world a whole lot greener and more efficient. So to truly make an IoT sensor useful, it needs a wireless link that takes off several crucial boxes. First off, it has to operate on minimal power to keep chugging along a single charge. Then it should play nice with mainstream wireless standards so it can seamlessly fit into existing networks. Plus, it needs to be independent of specific infrastructure, allowing for flexible deployment wherever it's needed. And let's not forget about the bidirectionality, which is the fourth requirement. Being able to send and receive data remotely for maintenance and updates is the key. Now, looking at the figure on the slide of intermittently powered device operation in the system without protection, even a tiny power hiccup can wipe out the network state, leading to unnecessary connections. But in the system proposed in the paper, things are working differently. The network state is actually stored and retrieved from non-volatile memory, meaning it can bounce back from power failures without skipping a beat, keeping those connections intact. Now, we'll see some of the existing solutions that the paper mentions and the limitations. So, even though we have got some existing solutions like backscatter based transmitters for LoRa, BLE, and LTE that handle the low power and compatibility aspects pretty well, they drop the ball when it comes to third and fourth requirements that were discussed in the previous slide. They just can't shake off the reliance on specific infrastructure, which limits where they can be used. And wake up radio approaches, well, they are out because they are tied down to specific setups. What's more intermittent? What's more that the intermittent operation of battery active radios leads to connection hiccups, resulting in wasted energy and constant reconnections. It's like taking one step forward and two steps backward. Now I'll look about the contributions of this paper. So in addressing these challenges, the study introduces three principal contributions. Firstly, the paper presents an innovative architecture for intermittently powered wireless systems. So this architecture meticulously checkpoints the system state for application, network, and operating system processes, ensuring robustness against power interruptions by employing ultra-low power timekeeping with microsecond level granularity. They achieve precise time management. Additionally, the architecture incorporates an abstraction layer, shielding the network software stack from power disruptions, thus ensuring a seamless operation. Now, secondly, the paper introduces the implementation of Freebie, pioneering bidirectional active wireless link powered intermittently. Freebie battery-free BLE mode demonstrates the capability to sustain a bidirectional Bluetooth link even during power outages. So this breakthrough guarantees uninterrupted connectivity, addressing a significant challenge in intermittently powered device operation. Lastly, the research enables the development of groundbreaking IoT applications by overcoming power constraints. These include the ability to conduct BLE firmware updates on intermittent power, so facilitating device maintenance and enhancement. And furthermore, they introduce a fully functional battery-free smartwatch, expanding the possibilities for energy autonomous wearable technology. Now, we'll talk about the background, like what went into the research and about the battery-free BLE nodes. So, the BLE nodes operate intermittently, meaning they are not always on, and their uptime can vary based on factors such as the time of the day, how they are positioned, and where they are deployed. To ensure the effective functioning of these, intermittently powered devices, comprehensive system support is essential. So firstly, control flow management is crucial to ensure that the device operates smoothly despite the irregular availability of power. Secondly, maintaining data consistency becomes paramount to guarantee the reliability of information amidst power interruptions. Additionally, environmental consistency must be maintained to ensure that the device performance remains stable regardless of external factors like temperature or humidity. Now, when it comes to enhancing battery-free systems, the usual go-to methods involve either beefing up the capacitor size or boosting energy harvesting efficiency. However, these solutions come with their own set of trade-offs. For instance, increasing the size of capacitor leads to larger device dimensions, while improving energy harvesting efficiency often translates to longer charge times. Both of these drawbacks can impact the practicality and usability of the devices. Now let's talk about the data transmission. While connection-less transmission might seem a viable option for intermittently powered devices, it's not quite as simple for protocols that rely on established connection. This limitation poses a challenge for maintaining communication in scenarios where continuous power isn't guaranteed. So now look at the framework requirement and um, of, like the first framework requirement of the paper that they want in the freebie. So the primary requirement for the framework is implementation of time-aware checkpoints and real-time restoration. This means that both the transmitter and receiver should have the capability to resume an ongoing connection without needing to restart if the power failure duration falls within the allowed timeout window. However, for traditional frameworks utilizing checkpoint-based or task-based approaches, so it often incur computation penalties, so leading to disruptions in the protocol timing. So the key insight here is to strategically trigger checkpoints at conclusion of wireless protocol process. By doing so, like it can be effectively like they can effectively sidestep timing violations and ensure the seamless operation of the framework. This approach allowed the researchers to maintain the integrity of the protocol timing while still providing the necessary support for time-aware checkpoint and real-time restoration. And the second framework requirement, which is the virtualization of time and peripherals. So the second like it's due to the intermittent nature of operation, both timekeeping and peripheral state can be disrupted. Therefore, we need a specialized software abstraction layer effectively mask or virtualize time and peripherals for the network protocol. The key insight lies in continuous powering of onboard time reference through a dedicated capacitor. This ensures that timekeeping remains consistent and peripheral states are maintained even during power interruptions. So by implementing this approach, they were able to create a reliable software abstraction layer that effectively masks the effects of intermittent operation on time and peripherals, thus ensuring smooth functioning of the network protocol. Now, the third and critical requirement for framework is dynamic handling of network connections. So this entails the ability to adapt connection parameters according to the available harvested energy, prioritize established connections or on-device computation and sensing tasks, and support preemptive scheduling for network processes. So the key insight lies in leveraging the adjustable connection parameters within network protocols. By dynamically adjusting these parameters based on amount of harvested energy, we can effectively optimize the use of available resources. Furthermore, by prioritizing established connections and on-device tasks, we can ensure that the essential functions are given precedence, even under fluctuating energy conditions. And additionally, supporting preemptive scheduling for network processes allowed the researchers to proactively manage resources and minimize disruptions. So in a sense, by intelligently using and utilizing adjustable connection parameters, the framework can dynamically adapt to varying energy availability and prioritize critical tasks and ensure the efficient operation of network processes in intermittent power environments. So now we'll talk about the architecture, and mainly this presentation is about the architecture and the framework design of the freebie that they have mentioned in the paper, rather than focusing on all the aspects such as the hardware and the required processor, RAM, and the like physical design. We are diving deep into the architecture. So the target network and device architecture. Uh, so it's all about that, like the intended network topology for the framework is star network, where communication is orchestrated through a wireless protocol governed by connection interval CI and connection timeout parameters. So in this setup, the host device may either operate through a tethered connection or with its own battery, while the end device operates as a battery-free entity relying on intermittent power sources. So the hardware configuration of the end device is logically divided into two distinct domains. So the processor MCU power domain and an always-on ultra-low power domain. So the latter is responsible for charging onboard capacitors and powering an external real-time clock, ensuring consistent timekeeping functionality. And the division of the power domains allows these for the efficient management of resources, with the MCU domain handling processing tasks, while always on domain ensures continuous power supply for critical functions such as timekeeping. So this architecture, in the next slide, I've shown a figure of the architecture, forms the foundation for reliable operation of a battery-free and intermittently powered end devices within the star network topology. So this is the network architecture that I was talking about, and so you can pause the video, have a look at it, and yeah, and as I explained, the network processes, real-time scheduler, how they are linked, and how time-aware checkpointing works. So next we'll move forward to time-aware checkpoints and real-time restoration. So in the architecture, the researchers have implemented time deterministic checkpoints, TDC as we call them, to ensure time-aware checkpoints and real-time restoration. So processes are classified into three categories, like network operating systems or application, each with its own subcategories of real-time or non-real-time processes. So this classification enables efficient management of tasks based on the timing requirements. To facilitate memory separation and structure, as illustrated in the figure below, the linker handles the task during compilation. It allocates static memory in distinct regions, ensuring that the memory is logically separated according to the process type. So additionally, a memory protection unit is employed to enforce access restrictions to memory regions that have not been restored, thus enhancing security and preventing unauthorized access to critical data. So this approach ensures that the architecture is capable of effectively managing time-aware checkpoints, real-time restoration, and memory protection, laying groundwork for reliable and secure operation in our system. So you can look at the figure, you can take a look, pause the video, and now we'll move forward to the process checkpoint scheduling. So at the heart of the architecture lies the process scheduler within the operating system. So this scheduler plays a pivotal role in determining the next power on moment based on the deadliness associated with the various processes. So during each power on cycle, the scheduler orchestrates three potential combinations of processes. So application only task, network only task, or combination of both the application network and network task. So the scheduler dynamically manages the restoration of the processes based on priority queue, ensuring that the critical tasks are executed in timely manner. So to provide a visual representation of this process, the figure below illustrates a power cycle featuring only the networking process. So this illustration serves the sequence of events and coordination between different processes during a power cycle within our architecture. And now we'll see the process checkpointing and restoration. So to ensure the integrity of the system, application network checkpoints, like they are consistently committed alongside an operating system checkpoint. This practice serves to safeguard against memory leaks and ensure the stability of the system. So the researchers employ a double buffered approach for checkpoints with dedicated memory regions allocated for each process. So this strategy optimizes memory utilization and facilitates efficient process restoration. So during like non-real time processes are dynamically loaded just before execution, and so this happens during operation. So it minimizes the resource usage. So in contrast, real-time processes are restored in advance with margin denoted as T restore. So this precaution ensures that the critical processes are ready for execution without delay. So in the event that the device fails to power up at the designated time, a recovery process is initiated. So upon resuming from power off state, the system begins the process restoration procedure as shown in the next slide. So this systematic approach ensures the reliability and reliance of our architecture even in the face of unexpected power interruptions. So this is the diagram that we were talking about in the last slide. You can pause the video and check out the diagram, and this is all about the architecture, the main architecture that we are talking about. So now we'll see the virtualization of time and peripherals. To achieve this virtualization, they implemented a virtualization layer position between peripherals and the network software stack. So this layer acts as intermediary, facilitating communication and synchronization between the hardware peripherals and the software components. So, following the restoration of real-time processes, the system synchronizes with the external real-time clock time at T-sync, signaling the resumption of real-time operation. This synchronization ensures that the system's internal clock aligns with the external reference time, maintaining accurate timekeeping functionality. So subsequently, T wake up, representing the next wake up time, is calculated based on T sync and stored in the operating system checkpoint. So this timestamp serves as a reference for scheduling the next power on event, enabling the system to efficiently manage power cycles and optimize energy usage. So through these mechanisms, our architecture ensures the effective virtualization of time and peripherals and facilitating seamless communication and operation within the network. Now, the dynamic handling of network connections. So the dynamic handling of network connections module offers two key functionalities: network recovery and dynamic network adaptation. So, firstly, in the case of network recovery, if a failure occurs but the device powers on before the connection timeout elapses, any missed connection events are bypassed. So, subsequently, the next connection event is scheduled as the protocol, ensuring connectivity and continuity in network communication without unnecessary delays or disruptions. And secondly, the network adaptation, the for the dynamic network adaptation, the module adjusts the connection interval based on the available energy resources. So when energy availability is ample, the connection interval is decreased to expedite communication intervals and optimize network efficiency. So conversely, if energy levels are low, the connection interval is increased to conserve power and prolong device operation. This dynamic adjustment ensures that the network protocol adapts seamlessly to varying energy conditions, maximizing the device's resilience and performance in different environments. So, in conclusion, the paper have presented a new architecture that enables battery-free operation of wireless communication protocols. The proposed architecture allows sustaining an already established wireless connection despite power interruptions. So the key components of this architecture include time deterministic checkpoints for time-aware checkpointing, real-time restoration, a virtualization layer for masking time and peripherals, and dynamic network handling for network recovery and adaptation. And this architecture enabled the development of Freebie, the first truly intermittently power active Bluetooth Low Energy system. So, and that is based on connectionless or beacon broadcast transmission. So overall, the work lays the foundation for the next generation of battery-free IoT devices with bi-directional wireless communication capabilities. So thank you for listening to this presentation, and thank you so much.